Good morning and welcome to session 15B, Uses Cases 2. We'll start the presentation given by Christian Braun for assessment of photovoltaic potential for building facades in Aix-sur-Alzette, Luxembourg.
Hello, good morning. Thank you for the kind introduction, and I hope you had a good sleep after yesterday's social event. Okay, I will talk about the photovoltaic potential for building facades in Aix-sur-Alzette, which is actually the second largest town in Luxembourg, situated in the southwest, close to the border of France. So, short outline. You may notice that results comes quite early, so I thought it's a good thing to put this first and to understand a bit better what we did and how the results look like. So, yeah, why did we do this? So the motivation came from a smart energy cities and regions platform. So our department is quite active in smart city topics and renewable energy potentials in the urban context. And so we thought about this secure platform. So secure is short for smart energy cities and regions platform. So we thought about this secure platform, and we take it on the urban scale. So we always try to look really on this kind of scale. So don't take a single building and do some simulation around this building, like lighting simulations, what architects are doing. So we take it on the urban scale and try to estimate the renewable energy potentials for the building roofs. This we did in the past already, and now it's about the facades. And also energy savings potentials, what's quite important in the future, because there are a lot of buildings that are not refurbished, and there's a lot of potential to save energy. Instead of just creating energy and put it on top of this energy wasting buildings, we try to also save energy and do not waste the energy from for instance, PV. So to do this, because it's the urban scale, really try to rely on distributed and high-performing computing approaches. I mean, if you're dealing with a city of almost 40,000 inhabitants and a lot of buildings, you have to have a bit more power. So we're working closely with the stakeholders, and we try to provide then tools, like I said, for PV potential of rooftops. Also, what I will show you now is about the building facades. And we also, like I said before, we have developed a tool for energy consumptions and savings of residential buildings. And we try to visualize the results in an interactive web-based mapping viewer, like you all know, like traditional WebGIS. So for the stakeholders, this means that we give them at hand some tools to accelerate the penetration of solar PV, of roofs and facades, and in total, we try to increase the energy efficiency. So something about solar irradiation. You can easily you can say that the global irradiation, which is received by a PV panel, what is shown here, is divided into two components, like the beam and the diffuse, and there's also some reflected parts, but this is usually neglected because it's really quite complicated to calculate, and it's not that much compared to the other two. So the easiest one is a direct beam on the panel, so it's a direct line to the sun, basically, which is not obstructed. There are no cast shadows in between, and the diffuse would be sunlight or energy coming from the sun, which is scattered in the atmosphere, like in small dust particles, like if it's very foggy, sorry, then light is scattered or even absorbed and either sent back to space, or it's diffused and then received as a diffused irradiation by the panel, which is not that much as a beam, but it's still there, and it can drive some electricity generation during the day if it's like cloudy conditions. Okay, so the beam components, of course, it's depending on the exposition and the slope of the surface, ideally the PV panel is directed to the sun, or averagely directed to the sun over the year. And also the slope. So in the northern hemisphere, usually the slopes are getting steeper, and here in the south, it's a bit more flat. Obviously, the atmospheric conditions like clouds, so if it's a cloudy day, you don't have any beam irradiation. And in general, the atmospheric transmissivity, like dust particles, for instance. And then if you have a lot of objects obstructing your direct view to the sun, which are casting shadows, that's clear. I mean, then there can't be any beam radiation, so an object is shadowed. And this is then also varying by the position of the sun, which varies over the day and over the year, what we all know, and also the topography and, like I said, the neighboring objects, like in a city, in an urban scale, it might be chimneys, antennas, other buildings, and so on. So this would be, it's very hard to see, okay. So this would be a first view, like you have a city model there with some blocks as buildings, and what you see here in the lower right, if you can see it, it's very hard to see. So there are the kind of sun positions over the year. So this varies over the year, and you can see that there are kind of compartments of sun rays, let's put it like this. So there would be your city center, and the sun varies every hour more. So these are all the hourly sun rays over a single day. So this would be 8 o'clock, the next one would be 9 o'clock, 10 o'clock, 11 o'clock, and so on. And each of these compartments gives you all the sun positions over the whole year. So that's like 365 days for 8 o'clock. So you can see that the sun position varies more from hour to hour than day by day, kind of. So, and the diffuse irradiation, if you imagine a picture like this, you're in kind of a valley in New York, and it's the so-called sky view factor, so how much can you see of the sky, which is then important to calculate the diffuse irradiation. So the portion of the sky you see is just at the end of this urban valley, let's put it like this, and just right above you. And to the left and the right, you don't see any sky anymore. And that's causes then a very low sky view factor, and the diffuse irradiation you receive at this point, at your viewpoint, is quite low because you don't have a view to the sky. Okay, and this is again this as a modeled phenomena. So you imagine that there is a kind of imaginary sky dome represented by all these points. It's kind of a regular grid, and for each point we calculate the visible part of from the wall. So we take we take a line from the wall point to every point of this kind of hemisphere or sky dome, and then by also applying some weighting factors, we can estimate how much diffuse irradiation is received on this wall point. So, and these are then the results. So this is the inner city part of Esch-sur-Alzette. And you can see already, so this is the global irradiation, so the total irradiation received over a year. So this is then in kilowatt hours per year. That's the unit. And so we take this CDGML apart and create a point grid on the wall, and then for each point of the wall we generate the global irradiation. So, and there's a lot of mass behind, and this is some kind of zoomed in area. Actually, that's the town hall here with a little place in front, little area, free area. You can see already that there over the walls, stretching over the walls, there's a nice gradient. So this depends then on the sky view factor, and of course the shadowing effects of the neighboring, in that case, buildings. So for instance, here on On the western side of the building, you see this nice gradient from blue to going to orange or even red, and this means that the blue are the lower values, and the red ones or the orange ones are the higher values. You can easily see that the lower parts of this building are not really suitable for putting PV panels on the facade, not on the roof. So we take out the roofs. Okay, so that's the math behind. It's a huge workflow what we did there, but don't worry, I will guide you through and explain you the single steps. So let's pick the low-hanging fruits first, obviously. So we come from some LiDAR data, what's in quite old LiDAR data set from the city of Esch, and we take the building footprints, and then we use something like the 3D Fire, which is a software of the Technical University of Delft, which takes building footprints, overlays it with LiDAR, and then extrudes this to an CityGML, which we also store in an open source project called the 3D CityDB. Yes, and from there we have this 3D view of Esch. So that's all the buildings, and what I showed you before, where this kind of inner city area here. These are large steelworks, for instance, of the ArcelorMittal company, and so on. So that's our basis to calculate with. So from there, from the CityGML, we wrote some PostGIS SQL script to take the building walls apart and generate this point grid, which we overlay on the walls. And from there, we can calculate the single intersections to the sun positions and the hemisphere. So we do this for every wall point. And in our example here, we generated a grid space of 1 meter. So for every 1 meter of the wall, we generate a point, and this then goes into the calculations. So this looks like this. So we have our building blocks here. It's a level of detail 1, CityGML, like I said before. And this is this point grid. So we kind of dissect the walls and generate the points. These are just a few because these were our example data set. Of course, it's there for the whole city. So the next one, also an easy one. We generate this kind of hemisphere, this sky dome, just the single points where we later calculate intersections from. That's quite easy and simple to do. This you also seen before. You see here this little patch. This would be the city of Esch. We just extruded these points to an imaginary, I think it's 100,000 kilometers or something, that they are really spread apart. And you generate this, finally, this sky dome. Okay, then it's getting interesting already because we want to calculate here at the bottom. It's the diffuse irradiation. First of all, I can mention this also already. We have nearby, we have a nice meteor station, which is actually a test site for PV panels where we have really good irradiation measurements, which are measuring the beam components and diffuse components of irradiation. And this we use as a reference to feed into our calculations. So in total, we generate for each of these points this sky view factor, and from there we can calculate the part of diffuse irradiation which every point receives. So this is again this intersection of this single wall point I show you with all these hemisphere points you can see from there, and this would be one patch of wall points attached with the sky view factor. So the dark blue ones at the top, you see more of the sky than the lower ones, because from the lower ones you have kind of your view is obstructed to the sky. Okay, and then what is also quite an easy one, so we take the coordinates of Esch and generate all the solar positions over the year. We use a Python script there called pvlib, or Python module, and generate all the sun positions over the year, which we then can intersect with the surrounding buildings. So this you saw already, okay. And so this one. Oh, okay, sorry. So we generate the solar positions, and then that's the most heavy part here in the lower left, to intersect all this lines from the sun to each point on the wall. This takes an enormous amount of time to compute. It's also very computational heavy. Actually, it's a single command in PostGIS. It's st3d intersect, so if some of you know this. And that's really heavy because we take every point from the walls and intersect it with, try to check the intersection with all the surrounding buildings in an area of, or in a radius of 400 meters. Okay, and this then leads to this stuff, and if you do the math completely, you get for every wall point, every meter, you get this representation. Okay, so you can see that, yeah, this kind of streets are facing southwest, receive some quite okay values. Others, like showing to the north, are the blue ones, which get less irradiation. They are not that suited. And others facing southeast, those are quite well. The red ones, orange ones are okay. You have here some quite nice ones. They're almost southly oriented, quite free, and they see the whole sky, and then they get quite high values. Okay, so some figures. The data is about 8,000 different walls, single walls of the buildings in Esch, which makes up to 3 million wall points. And we generated 1.2 terabyte of auxiliary data, so these are all the intersection tables. This is not necessary to keep them, but as this is work in progress, we need to keep them and check the results. So the whole computation is parallelized, of course, otherwise it would never finish. So we use quite a big machine with 70 CPUs, and this takes about 10 days of computation time to generate the global irradiation for this part here. So that's actually the biggest machine we have so far. Otherwise it would be a bit shorter. So advantages, it's mostly based on standards. So the storage of the data is done in, on the one hand, it's a CityGML we generate. We also could use higher level of detail CityGML with some roofs included. And we import this into the 3D CityDB, which is also quite standardized. They have a nice data model to incorporate every features of CityGML, which is actually a landscape model. Also, it's called city, but it's a real landscape model, so you can model trees, bridges, roads, water areas, and so on. And this 3D CityDB, if you import it, if you import the CityGML into the database, then it keeps the semantics, so everything is there still, and you can assess it with your scripts. That's very good. So for the computation, it's one main Python script which kind of fires SQL queries to the database, and this is then parallelized. We can also distribute it to several machines, so this is also there. So we dissected like the downtown area of Esch in several smaller parts, and you could spread this to several machines, and later on just pull everything together, and you reduce your computation time. Yes. So some outlook. It's very short actually. What we need to include is still the topography. So if you have hills around, which are surrounding your area, for instance here in Gimaresch, this would be very useful to get the shading correct. Also the vegetation, like trees standing in front of a building, which are shading the facade. This is not in yet. We want to extend to the roofs as well. We had some other approach dealing with our sun. So we did it already for the roofs, but not in 3D. It's just a 2D or 2.5D approach with a surface model, also derived from LiDAR data. And important for the stakeholders is then to build up a kind of economical model for the placement of the PV panels. So we need to do something where we dissect our facades and highlight the useful parts of the facades. We also need to think about how to take out window areas, for instance. Also quite important. Yeah, we have done with the best data we can get, and this is then, for us, the state of the art. So if we would get a higher level of detail CityGML, then this would be better, obviously. Okay, So that's it. Thank you for your attention, and if you have any questions.
Thank you for your presentation, Christian. Any question? No? I have just one.
Yeah.
This is a complex computation, but do you think that it's possible to integrate in a GIS software, some kind of algorithm, since it is built in Python, and do you think it is possible to do that?
Yeah. I mean, it's just more or less a Python script and the database behind on a quite a huge server. So to control it, you just need a single Python command, and then everything runs more or less.
I see that the Skyview Factor, the Saga GIS software, have some algorithms that perform that, for instance. So do you think that it can be possible?
We implemented it that way, and we have some equations behind. It's quite a robust and very old model to come to the irradiation. And the Skyview factor is also there, and I mean, it's just a few equations actually, but you have to put together all the data, and that's the more challenging part. So it took us some time to get everything right, and then to scale it that it really runs in a decent time. Because if you do this on kind of one CPU, if it's not parallelized, this will take, I don't know, several years to finish. So.
Okay. Thank you again, Christian.
Thanks.
Let's move to the next presentation given by Nathalie Guimarães, development of a web application to provide and analyze geographic information within the scope of the Interact project.